All right, so good morning, everyone. We are regrouping after a long time, but let's hope to make some good progress this week and the next week so that we can get started on homeworks, assignments, and there will be a small course mini project. So if we can cover enough base these 2 weeks, we will be able to get started on these assignments and homeworks. All right then. So yeah, if you have any questions, please feel free to put it in the chat box. While you can unmute yourselves, the voice on my system is not quite good, so because of that, I have challenge exactly hearing catch what you're saying. So feel free to use the chat box. And well, so our goal is to let's see. So given a program, so as if you remember in the last class, we ended the last class by saying that so far we have been programming for correctness. Okay, so we are programming. So far we have been programming for correctness. And now in this course, we want to not only program for correctness, we want to focus our attention on programming for performance, how we can improve the performance of a given program. So that is the challenge that we are setting forth for us in this course. So in this process, like first you write a program and you check if that program is correct or not. So that is the first step, if you think about it. So for a pre-step, so the first step or pre-step or step 0 is check the correctness of the program. Once you write the program, you check the correctness of the program. So once you check the correctness of the program, and then now we want to see how to improve the performance of the program. And in order to improve the performance of the program, the thing that we have to do is we would like to measure the performance. We would like to measure the performance. And to measure the performance of the program, we have to profile the program. Okay, so we have to run the program and see what parts of the program are taking substantial amount of program execution time. So we profile the program, and once we profile the program, we identify bottlenecks. What are the bottlenecks? Identify bottlenecks in the program. This is the second step. And of course, after we identify the bottlenecks, we would like to improve or remove the bottlenecks. We would like to improve the performance. Improve the performance by removing the bottlenecks. And then we repeat this process until we are satisfied with the performance of the program. We iterate. Until we are satisfied, we keep iterating this process. So in this process of, there are two parts here. the first part is how do we profile our program? We will spend some amount of time in today's lecture on this first step. This is correctness, no, this is step 0. And so step 1, we will spend some time on how do we profile our program. Second, of course, identifying bottlenecks. We analyze the profile and try to identify the bottlenecks. That is step 2. So this you will learn. This is a very, step 2 is not quite easy. So it takes quite some time and experience to get there and to go about systematically identifying these bottlenecks. And of course, step 3 is also a challenge. And when we think about step 3, for example, what are all the options that we have to improve the performance of a program? Okay, so once we have identified bottlenecks, what are the options that we have to improve the performance? Like, for example, you may want to go and change the algorithm. You're not happy with the algorithm. Right now, you are using an algorithm which takes a cubic time, and we would like to come up with an algorithm which takes, let's say, maybe quadratic time or n square log n time. So you want to improve the complexity of the algorithm. That is one option. Maybe that is the algorithm that is the best that you have, and perhaps the way you are writing, you have written the code, it may not be quite optimal. So you may want to improve your data structures or do something about your code so that you can get better performance while the complexity of the algorithm remains the same. It is quite possible that the 2 students or 2 engineers write code for the same quicksort code, but the performance of one version of the code is substantially better than the performance of the other version of the code due to some due to the particular way in which the code has been written. And then after that, we can try compiler optimizations. Okay, like for example, you can compile your code using the -02, -03. And if you see man GCC, there will be whole bunch of optimizations that are possible. Like for example, you can invoke specific inlining strategies, loop unroll strategies. So your compiler can do a lot of things for you. You can try this also. You can try, so how you can use compiler and try to improve the performance of your program. This is also very challenging task because there are so many options. If you see man GCC, there are so many options, and these optimizations, they interact with each other in a way which is not easy to understand for us. And so navigating through this space and trying to figure out what is the optimal, what is the right combination of optimization flags we should be using so that we get the best performance for our program is also a nice, it's also a path we should explore to improve the performance of our program. Compilers typically do what are called as scalar optimizations. What are called as scalar optimizations. So an example of a scalar optimization is, for example, you have written the code as area is equal to 2 times pi times r. Sorry, this is circumference, right? So okay, so whatever. Circumference is equal to 2 times pi times r. And pi, you may have defined a macro for pi because you want the code to be modular. Then what happens is when the code gets generated, so that this is circumference. So what happens is this gets transformed to 2 times 3.14 or whatever times r. And what can happen is during the execution of your program, every time the multiplication, floating point multiplication is issued to multiply 2 and 3.4, but we know 2 times 3.4 is 6.28. So unnecessarily we are spending cycles when the program is executing. And think of this statement being in a loop. So the overhead that this generates, it will be multiplied by the loop trip count. So by the compiler, it can fold this. It figures out 2 times 3.4 is 6.28, and it can automatically, it can eliminate this fmul operation. So these are the kinds of things which your compiler can do. And yeah, so this is about compiler optimizations. We don't spend much time. Perhaps I may give one assignment on how to, where you try to optimize the performance of a program by enabling or disabling flags. So I will give one homework on this problem, just so that you get some experience. Or you can use the SIMD lanes, that is, vector instructions. Your processor might be able to add, like for example, 1, 2 plus 4, 6 is equal to 5, 8. This is not two operations are happening in parallel. This is what is called as a SIMD extensions, your single instruction multiple data stream. So your processor might be able to do that. So you may want to use the SIMD to improve the performance. Or you can use multiple cores. Your system may have 4 cores, 6 cores. How you can use the multiple cores. And then how do you use the cache? Locality is an important thing. How can you use the cache memory properly so that you can get the performance out for your system? And after you try out all these things, maybe you may want to use a GPU, you may want to use a TPU. TPU stands for Tensor Processing Unit. GPU stands for Graphics Processing Unit. So if you see all these things, there are so many possibilities, starting with algorithms, rely on compiler, use SIMD, use multi-core, use your caches properly, use the accelerators that are present on your system. You have to explore all these options to see how you can improve the performance of the identified bottleneck in your program. So this is the challenge. But then before you set on this journey and try to spend a lot of effort in getting there, you may want to see what is the theoretical best speed up that you can get for your program. Like for example, if you think of your program has this is your program. Your program has some serial part. Let's say the fractional S is the serial part of your program, and the P is equal to 1 minus S. This is the fractional so if you think the whole program as one program execution time as 1 unit, fractional S part is serial, and the P part, that is 1 minus S, it is parallelizable. Okay, you can parallelize it. It is amenable for parallelization. And if you think about it, then what is the maximum speed up that you can get? So if you want to compute speed up is the baseline is this is if you S is the serial numerator, the serial version of the code, plus parallel version of the code. So parallel version of the code, it has S plus P by N, where N is the number of cores that we use for parallelization. We are assuming ideal speed up, that's all right. Okay, we are assuming an ideal speed up. So here, did I get it right? I think I made a mistake here. Let's see. The numerator, the serial, we are assuming 1 unit. 1 unit, or in other words, if you put it, S plus P is the denominator. This is no parallelization in the denominator. No parallelization in the numerator. And then in the denominator, we are trying to parallelize our program using N cores. And if you think S plus P, the whole thing as 1 unit, that's what we are doing here, then this is equal to 1 by S by. So P is equal to 1 minus S that we are anyway having. So the important thing here is, as the value, the amount of speed up that you get, as n tends to, if you compute limit as n tends to infinity, capital N tends to infinity, the speed up that you get is 1 over S. That's what you get. That is the speed up that you get. So the amount of speed up that you get, like for example, if the whole code is completely serial, then S is equal to 1, then the speed up that you can get is just 1. That means you get no speed up. But on the contrary, if S is equal to half, S is equal to 1 implies no speed up, there is no speed up. Speed up is equal to 1. And S is equal to 2, that is, S is equal to half. That is, we are talking about. If S is equal to half, then speed up is equal to 2. This is a max speed up that you can get. So if you are expecting a program that, let's say, if 50% of the program is serial, and you are trying to get your program to run at 3x speed or 4x speed, then it's a hopeless endeavor, right? So that is what that's an important realization that, okay, this is the best possible speed up that I can achieve. So this understanding you should have. This understanding you should have. In order to see this, let's take a look at, I'll share it with you on my desktop. And please feel free to ask questions, stop me and ask questions. No, we'll keep it informal and have fun. So if you see here, you can see this is, let me run this. So this is what we just looked at. This is what is called as an Amdahl's law. So let's say if your program out of 0.1 fraction of your program is serial, and that means P is equal to 0.9 fraction of your program is parallel, then if you see, then the speed up that you get here, you are seeing here, this is y is equal to 1.0, that is the whole program execution time, divided by S plus P over N. So we have P over N because we are using N cores to parallelize the parallel part of your program. There is a question here. Can we find S for an arbitrary given program? So we will see, Balaram Krishna. So it's a good question. It's not easy. Okay, we have to profile the program. Like for example, if you see here, when S is equal to, let's use S is equal to 0.5 and see what happens. When S is equal to 0.5, you can see if you use the maximum speed up that we can get, up to 9 cores, the maximum speed up that we can get is approaching is bounded by 2. It is bounded by 2. That we have already seen, right? So that's the example that we have seen before. And if I make it 100 cores, even if you increase the course, then also it doesn't matter. So you can see it is approaching. This is called as Amdahl's law. Okay, as you increase the number of cores, it doesn't matter how many number of cores you use, the speed up that you can use, that you can get is bounded by 2. And this is given by the amount of parallel section that is present in your code. So for the same 100 cores, let's say if we increase the serial, if you decrease the serial section to 0.1 and increase the parallel section to 0.9 and run it, then you can see that the parallelism, that the speed up that you can expect is around up to 9. Are you with me here? Does this make sense? So given a program, you need to check what is the maximum achievable speedup for your program. Yes, no? Are you with me here? This particular idea? This is a very famous thing called as Amdahl's law. All right. So now the second, there is an important extension to Amdahl's law, which is called as Gustafsons law. So I suggest that you read about Gustafsons law later. But the idea in Gustafsons law, in Amdahl's law, we assume that that the program, that the amount of data that the program processes, or the scale of the problem that a particular problem solves, it always remains the same. Like for example, but it need not be the case. What happens is, as the compute resources available for us increases, then we might be able to we may end up increasing the scale of the problem that we are solving. Like for example, I heard from one of my colleagues earlier that they do some kind of analysis on the amount of radiation which an antenna gives or something like that. While doing that, they tessellate the space and try to find out how much signal strength is there in a particular cell, etc. And the size of the cell they take depends on the amount of compute power that is available. If the amount of compute power that is available is, let's say, one big server, then the granularity of tessellation will be at some level. But on the contrary, if the compute power available is much larger, you can tessellate the space at a much more finer granularity and get better results. Can you think of any such examples that you have encountered? Any examples that you have encountered like this, where the problem can perhaps be scaled if we have more compute power available? Come on, guys, sleeping? Awake, awake, talk. I would like to hear from you, learn from you. So one example I thought of is, machine translation is a very important area of research. So where we translate sentences or text from one language to another language, English to French or English to German, vice versa, or Telugu to Hindi, Hindi to Telugu, etc. In these machine translation approaches, especially the latest statistical techniques-based approaches for machine translation, they rely heavily on a lot of training data. Okay, so the greater the training data, if you can, instead of training your model using 1 lakh lines of translation text, if you use 1 million lines of translation text, then you will get better accuracy in the translation. So that's how Google does pretty good at machine translation, because they have access to huge amount of this training data. And not only that, they have access to huge amount of training data, they also have access to they also have access to a lot of computing power. So because of that, they will be able to build very accurate machine translation models. And this is generally true in all machine learning. If you train the model with lot of data, you will get better accuracy. But of course, it depends on the availability of data, number one. Number two is, so availability, yes, availability of data and availability of compute power. These are the 2 points. So Balaram Krishna has an important things. Computer graphics, when you increase the depth of recursive ray tracing, we have more number of GPUs. In computer graphics also, when you want to do animation, if you want to get an extremely good quality animation, then you may have to do more computations. Like for example, I heard some time back a researcher in computer graphics, he was telling, Disney maybe a decade back or 2 decades back, 2 decades back, when a princess is moving, there is this cloth which kind of floats in the air. They may use some rudimentary techniques or a sequence of images to kind of show that flow of the cloth behind the princess. When water splashes, you use some rudimentary technique to show how water is splashing. But if you use a physics-based simulation for water splashing or the dynamics of airflow, then you get a more interesting animation for a cloth floating in the air or water splashing. Okay, this is true even for your gaming, right? So all the games that you play, so if you want to get a more realistic animation, then a greater amount of simulation needs to be done, and it correspondingly increases your compute power. Are you with me here? You understood? So this is an important idea because the problem size is not fixed here. The problem size is fixed because the available compute power is fixed. But if there's a greater scope for compute power, perhaps we can expand the scope of the problem and get more accurate results. All right. So let's say you have this is in order to understand this Gustafsons law. So let's say you have a program which takes S plus T time to execute. The total time taken by a program is S plus P time to execute on a machine with n cores. On a machine with n cores, if you see here, this is S plus T. This is the parallel. So serial execution time, serial divided by parallel execution time. So here, the parallel execution time, it consists of S plus P, and this P is, like there are n cores. There are n cores are present, and each core takes P units of time. Each core takes P units. Each core takes P units of time. So since all these things are happening in parallel, the combined execution time is only S plus P. Okay, it is S plus P. That is what we have in the denominator. But if you do this on a serial machine, the total amount of work that needs to be done is S plus NP, because there are n cores that are working in parallel. So the total time taken is S plus NP. So if you take serial divided by parallels, yes, serial is in the numerator S plus NP, and in the denominator we have S plus P. And if you so the whole S plus P, of the if you take it as one unit of execution, we get 1 in the denominator. Okay, so now you can see that the speed up that we are getting is equal to S plus NP. This is the overall speed up that we are getting. So as the amount of work increases, it is possible for us to get very good speed up because this capital N is there in the numerator. Okay, so keep that in mind when you are working on a particular problem. For some problems, Amdahl's law could be applicable. For some other problems, like when you are working on machine learning problems, training, especially training algorithms for machine learning or certain kind of animations that you are doing. So the speed up that you may get is you can expand the scope of the problem if you have more compute power available to get more accurate results or a better version of better looking cartoon, for example. So are you all with me so far? Let's check. I'll take a pause here and see how you are doing. Gustafsons law and Amdahl's law. This is where we are now. Yes, no. Vikram, Vidit, Sudhir, Shreyas, Aditya, Akash. You're all doing good. Okay, good. Now, let's move to the next important part. Okay, that is how do we profile the programs? Did you guys ever try to profile any program? Profiling a program. How do you think you can profile a program? Time complexity, memory complexity, that's a theoretical analysis of the program. But if you want to really figure out, like, hey, this much amount of time, you have a big program that is executing. So you want to figure out, where you want to understand your program and see where the time is being spent more. Time and memory complexity do give an indication, but so any other tools you use it for profiling a program so far? Okay, so let's see. Did you ever use time command? We can have a CPU, GPU usage, which is incremented each time and print that in the terminal. It tells us, okay, good. So Balaram Krishna is mentioning like how we can annotate the code, source code, so that you can figure out which functions are called more frequently, etc. No. So even before you do this, let's say if you are profiling your program, or if your program is not performing well, generally you run the program and you feel, okay, the program execution time is bad. What is the first thing that you should be checking? What are the couple of things that you can check? Two quick things you can do. The two quick things you can do, you do a H-stop and see the load on the system. If the CPU is completely hogged, okay, all the cores are completely hogged, and when you give your program for execution, there may not be any problem with your program. It's just the load on the system is very high, and your program is not getting sufficient compute time. And because of that, it is running slowly. Okay, so the first thing you should check for is load on the system. Check for load on the system. This tells us whether other programs are interfering in your program execution and affecting its performance. That's number one. Number two is, it's very simple. Like, like for example, if you want to, we can just say time ls. Okay, you can use the time command to check what is the wall clock execution time of your program. So these are the super simple things you can do quickly to get a hunch about how your program is executed. Okay, like for example, let me take, let's go here and let's see, there is this program called as GCC collards.c. We will, so don't worry about what that program is, but let's say you want to understand want to do some baseline profiling. You can see, at the end, this is the output of the program, whatever you are seeing, don't bother about it. But if you see, it tells us that this program took 355 milliseconds for execution. This is the wall clock execution time. And out of the 355 milliseconds of execution, 343 milliseconds are spent in the user space. And 12 milliseconds are spent in the system space. So this is very good because, like for example, let's say if you are working on a program which involves lot of I/O or network activity, lot of time you may end up being in the system space or in the kernel space, waiting for the I/O to happen, input output to happen, or network, or waiting for packets. In which case, the system time could be larger than the user space time. The kernel space time could be larger than the user space time. So this is a quick rough idea about how about what is happening in your program. What's the problem with this approach? Akash, what's the problem here in this approach? Is there, this is good, but is there any issues, problems in this approach? Aparna? Yeah, you don't get a breakdown of what section is taking more of the time. So that's the problem. You don't get a breakdown. So how can you, so that's the challenge actually. So if you just take time, you don't get a breakdown, but we need to know what sections of the code are taking more time. In order to do that, so we do what is called as a program profiling using, for example, GCC provides a tool called as gprof. Okay. So if you see, this is the code. We are here, collards.c. This is some program. You don't worry about it. All you need to see is, broadly speaking, the function main calls the function seq 5 lakh times, and then this function seq in turn calls this step function. This is how this program is structured. And so let's see, this is the program that we have just run, and we want to get a deeper analysis of where what is happening. And in order to do that, so we can compile this program using this option called as -pg. Okay, -pg collards.c -o collards. So once we instrument, so when we do use this option -pg, what happens is when the program is compiled, then GCC inserts some instrumentation code into the program. And this is the instrumentation code which Balaram is suggesting that we should insert by using static variables in a function. But if you think about it, if you go and do that, you will be all over the place. And then later on, you want to remove them and all sorts of challenges will come. But if you use -pg option, then no, GCC automatically instruments the code. This is what is called as a compile time program instrumentation. So what we are doing here, please remember, these are very important ideas: compile time program instrumentation. And once the program is instrumented, you can run the program. And after you run the program, so you have to use this tool called as gprof, collards, gmon. A file called as gmon.out will be created. And when you run this, this is the profiling information that you get. So this is the profiling information that you get. That how many times main is calling nseq, nseq, and how many times nseq is calling step. All this information it will print. We don't need to explicitly insert static variables to do this job. But if you see this information, gprof, the information generated by chiefprof, it's not very, it is good, but you need to learn, you need to spend some time or gain some experience trying to read it appropriately. Like, for example, at least the simplest thing that we can say is, out of 100% of program execution time, 91% of the time is spent in nseq function, and nseq, and out of that 90%, 91%, 40% is spent in the step function. So we are getting a nice breakdown of how much time is spent in different functions in this program. And and then we can try to focus our attention on maybe if we try to speed up the step function, we might be able to improve the performance. Okay, so you can kind of get an estimate using Amdahl's law if 40% of the code is sequential, and if we somehow can improve that 40% of the code, this is the expected speed up that we can expect for the collards program. And so I'm not going to explain in detail how gprof tool works. Of course, you can read man gprof. If you read man gprof, you will see lots of interesting flags that you can use, lots of ways that the information can be displayed so that it becomes easy for you to read that information. But one important thing I would like to highlight is this particular approach of profiling a program is called as a program instrumentation approach. So you compile the program, and when the compile is programmed, when the program is compiled, the compiler automatically inserts some instrumentation code, and when we run the program and all the statistics it generates, they will be generated in files. Like for example, in the case of GCC, it generates in this file called as gmon.out. This is the place where it generates. So the challenge here is since these counters are inserted in different functions, there could be some overhead when we execute the program. Some minor overhead will be there. Another approach for program profiling is so do you remember from our CPRO class that we use Valgrind for checking memory leaks? But you can use Valgrind for doing like profiling the code also. So we can use, like for example, Valgrind -- tool callgrind /collards. You can see, did you notice anything interesting between the previous program run and the current program run using Valgrind? Anything interesting? And here the interesting thing for me is my CPU, the fan went up, and the fan on my CPU started making noise. There is no compile. Interesting thing, I would have been very happy if you were here, because after the program exited, my CPU fan, it went down. The sound, it's no longer making the sound. So people can do what is called as a side channel attack based on the sound that here, whether how much compute workload that you are using, etc. Okay, we don't need to use minus PG actually. Let's do one thing. We should not use minus PG. Yeah, so we don't use minus PG when we are running it Valgrind. Let's try to run it again. Now again my CPU fan, no, it's going up as the program is running. And it is going down. Awesome experience for me here. One thing you should have noticed is no, the program took a longer time to execute. The reason is Valgrind is like a virtual machine. So Valgrind is like a virtual machine. It executes, no, it reads the instructions of the program and executes it by itself. Because of that, it gets a complete control on all the statistics that it can collect. But when it acts as a virtual machine and tries to interpret the instructions, every instruction at the program level, if it gets executed in the hardware, it will take around maybe a 1 clock cycle to execute. But at the Valgrind level, it will take perhaps a few tens or even hundreds of clock cycles. Yeah, perhaps, yeah, that's true. So now, once are you with me? Do you see the difference between minus PG option, gprof approach, where the program is instrumented? Right now, we don't need to instrument this program, but what happens is Valgrind is a virtual machine. It intercepts every instruction of the program and carries out the execution by itself. And because of that, it can compute very detailed statistics. But the problem is it takes time. So here in the CPRO course, we use the memory tool to analyze the memory profile of the program. But here we are using call grind tool. Later on, there is something called as a cache grind tool, which you can use in order to understand the memory behavior of the program. How many cache misses are there? How many cache hits are there? And all those things you can analyze using the cache grind tool. So you can, so there are multiple tools which kind of or work together with Valgrind, and each of them they try to do different job. So right now we use call grind because we want to understand the profile of the program. And if you run this tool called as cache grind, let's see here call graph. If you see the call graph of this program, not here, let's go up. Yeah. So see the call graph. How do I? So main calls so main calls NCQ and NCE calls step, and how much percentage of time is spent in each of these functions. We get a very clear call graph picture, and using this we can understand what are the bottlenecks in our code. Also, I don't understand why source code is not coming. Call graph parts. Call. See 80% or 50%. Caller map, machine code. Did we compile the program using minus G option? Yes, no? Because it's not showing the source code, because it is possible for us to get it assumes some instruction set, some memory hierarchy, and it is giving the cache misses also. You can see the number of last level references, how many misses are there, how many hits are there, all this information also we can update. Where is, I'm trying to see, view, go settings. For some reason, it is not showing the source code here. It is possible here, if you go here, and you look at the source code, it clearly shows this particular line in this program. It is making a call to step this many number of times. And that is a very useful piece of information. Okay. Anyway, so my goal again is not to teach you how to use this tool. I want you to be aware that these powerful tools are available, and every tool has their pros and cons, and you have to understand the pros and cons and use the tool appropriately. What is the primary disadvantage of the Valgrind? And what is the advantage? What is the disadvantage and what is the advantage? Aparna, Gautam, what do you think is the overhead is where is the overhead coming from? The overhead is coming because of the virtual machine, exactly. And the advantage is we can get a very detailed profile. So usually when you are doing for big problems, using Valgrind is a bit of a challenge. Okay. So now we will move on and we will look at one more approach. So this is by using a tool. So modern processors, they have what are called as hardware performance counters. Hardware performance counters. So using this any processor, it will have some 4 to 5 hardware performance, maybe 4 or 2 to 4 hardware performance counters. Using these performance counters, it is possible for us to monitor different aspects of the program. But the way these hardware performance counters work is by using what is called as a sampling-based approach. So let's say if you want to monitor some 10 events, but the available hardware performance counters are only 4 registers, then what happens is automatically you don't monitor, the system doesn't monitor your program continuously. It samples it at different times and try to get a sense of what is happening in your program. So, but the cool thing about hardware performance counters is it doesn't interfere with your program performance. That's the important thing. And you don't need the source code of the program. Like for example, we can see perf stat collapse. And we need a sudo permission to do this. I have to do. See, so now when we ran collapse, you can see that 0.993 CPUs are used. So immediately you can say this program is not a parallel program. You don't even need to look into the code. You don't know whether the person who wrote that code parallelized the code or not. But when you see, you can see that this program used less than 1 CPU. And here you can see that it says as this program executed, there are 47 context switches, and there is one migration, that is, my processor has 6 cores. So the program migrated from one core to another core. So it happened only once, and the number of page faults. If you're working with programs which are IO intensive, the number of page faults could be high. Or if the working set size of your program is much larger than available memory that is there, then the number of page faults will also go up. You can see many other statistics here. And the instructions executed per cycle, 0.98 instructions per cycle. So that means your program doesn't have good instruction level parallelism also. Typically, we would like to have at least greater than one instruction per cycle, but here we are executing it at 0.98 instructions per cycle. There is one more thing I am a bit surprised. It is saying, no, my processor is executing at this gigahertz, but it cannot be the case. I don't know why it is saying, because I didn't, the baseline frequency of my processor is some 3.2 gigahertz, something like that. And I didn't configure my processor to boost to a higher frequency automatically. So this is a bit of a surprise. And you can do lots of other things for stat. Let's see, -d. Yeah, so you can see you will get also a cache analysis that the number of cache misses, L1 D cache. D cache stands for data cache. So this is the total number of loads, and out of these loads, this is the number of misses. D cache misses, and this is the LLC loads. LLC stands for last level cache, and this is the number of LLC loads. So again, what I want to point to you is that this is using hardware performance counters. You can monitor your program in a non-intrusive fashion. And we use a technique called as the underlying technique is called as a sampling based approach. So you don't get quite accurate results, but depending upon the number of events that you are monitoring, you will get a decent estimate of what is happening in your program. So if you think about it, with respect to hardware performance counters, two things. Advantage is we monitor the program in a non-intrusive fashion. There are two things that we have to keep in mind. Since it's a sampling based approach, the accuracy, we have to check if the results that we are getting, that the profile results that we are getting is accurate or not. That is number one. Number two, that is of concern. What is the second problem, potential problem here? Is there any second potential problem? Sairaj, what is the second potential problem? It can differ greatly based on the load on the system, of course. That's true. Well, may not be because these stats are collected only for the process. That is the thing. But the bigger thing is this is a profile of the whole program. You don't get the profile for that compute intensive part that you are looking for. Let's say there is a hotspot in your code and you want to optimize that, you want to understand the properties of that code. But when you do use a perf and do, you get it for the whole program, but you don't get it for a section of the code. Make sense? Okay. So this is about hardware performance counters. And now there is one more tool which is called as a pin. The tool name is called as a pin. which does what is called as a dynamic binary instrumentation pin, which I don't know whether it's a dynamic binary instrumentation. It does binary instrumentation. That is, it takes your executable and it puts some hooks into your code and tries to collect some profile information. This is a very, very powerful tool. And I'll just show you one example, one very interesting example for pin, application of pin. Let's say you are running your program, or there is a program that you want to execute and understand what are the properties, like whether it's whether the compute intensity is coming from integers or it is coming from floating point numbers you want to estimate. So in order to do that estimation, it is a very, very painful job. Even earlier Balram was mentioning you can insert static variables in the program and try to estimate the function called frequency. But that approach also doesn't quite work if you want to get an estimate of how different instructions, the distribution of different instructions when a program is executed. How many floating point instructions, how many branch instructions, how many integer instructions, all these things we would like to get. We may not get an estimate of it. So we can do it using the spin tool. So this spin, so let's see more. This is a very complex tool. I will just show you the usage by looking at an example from its installation. So now here we are trying to understand the distribution of instructions when we execute ls. Okay, so you are kind of looking into ls, taking an X-ray of ls. You run this. Okay. To build, where are we? Oh, okay, it's run. So it recorded the output in this file called as, where is that file? Opcode mix.out. This is the file in which the results are recorded. So now let's look at more opcode mix.out. You can see, like the add instruction is executed 7,000 times, and AND instruction is executed 5,000 times. Call instruction, compare instruction, what is the distribution of different instructions, and there is one fadd instruction. You can see that in this when we run this ls program, it's not floating point intense, so all the floating point instructions are executed in less than, the frequency is less than 100. Does it make sense? Are you with me here? So how we can quickly, on the contrary, if you run a different program, okay, maybe I'll try to run instead of /bin, let's see, /PFP22 collards code. So more opcode.out. This is the instruction frequency. And let's see here also, you don't see any floating point instructions executed, very few in number. Predicated and unpredicated. Where is it? Count unpredicated, count predicated. Not sure with it. Not sure. Let's run one more program. Code saxp. Yeah, so here you can see that there is I'm not sure what is happening. So we have to understand essentially. So what is going on? So pin is, this is one example of pin. Pin, there are so many tools which are just like Valgrind. There are several things that are associated with pin. Like for example, you have this call graph.py, and then there is this call trace, there are flow graph, instruction count. There are a bunch of tools which are associated with pin, and you can use these tools in order to get a deeper understanding of your program. Okay, are you with me here? Are you all with me so far? What are all the tools that we have learned today for profiling? Can you list? Can you put in the chat box? Let's see what is the first tool that we learned. First tool. Time learned, gprof we have learned, and then after gprof cache grained, yeah, gprof gcc minus pg, that is okay, and then perf pin, so while all these things are good, there is one thing we still not h-top. Yeah, there is one thing that we still didn't figure out. That is, if you want to measure the execution time of a particular function, you know, like for example, you are working on a matrix multiplication problem, and you want to understand what is the time taken by that particular function. So in order to see, let's open this. Let's say I have open this open folder. Okay, so later on we will study, we will look at what is called as a BLAS library. So in BLAS library, one of the problems that is there is what is called as it's a vector multiplication problem. There is what is called as a, let's see, driver.c. Okay, so there is this problem where we have, if you see, we want to do this computation, y is equal to a times x plus y, where y is a vector, 1 to n, and you take a and you scale the vector x, and then you add the vector here. Okay, a times vector x plus vector y, and store it back in y. So this is what is called as a BLAS, stands for Basic Linear Algebra System. This is, there are 3 levels of BLAS, and at every level of BLAS, there are some kind of problems which fall under that level. And at BLAS level 1, we work with operations involving only vectors. At BLAS level 2, we work on matrix vector problems. Like matrix times ax is equal to y. This is a matrix vector problem, right? And BLAS level 3, this is here we work with the matrix problems. Like for example, we want to compute the product of 2 matrices and compute C. So right now we are looking at a BLAS 1 problem where we take a vector and we multiply it with a scalar and add it to another vector. So if you see the code here, the whole code is divided into multiple C files. The first C file is the driver file, and so here we are allocating we are setting up the system. We are setting up the system from here to here. We are setting up the system. We are generating on line number 31 and 32. We are generating two random vectors of size n. Two random vectors of size n. The default size of these vectors is 1 million, which you can see on line number 8. And if you see here, if there is an argument is given, we take that argument as the vector size. Otherwise, we take the default vector size. Okay, so this is the plan. So if no argument is given, the default vector size is 1 million. But if an argument is given, we take that argument as the size of the vector. All right. So, and then we allocate from the heap, we allocate two vectors. And so we assign, we initialize these two vectors to random vectors. So if you go and see helper.c, in helper.c, this is the place where we are generating these random vectors. Now I understand the problem. I have no problem. Good. So we are initializing this two random vectors. This is there in helper.c file. And helper, there are two other helper functions. One is called as a tick. So to tick, we pass a time val structure, pointer to a time val structure, which takes a snapshot of the current time. And when we say talk, that is when we press the stopwatch, then it computes the total time elapsed since we started the stopwatch. Okay, to start the stopwatch, we do a tick, we call the tick function. In order to stop, we call the talk function, and it returns the number of seconds elapsed. So here, what we are doing here is, if you go see driver.c, so this is the place where we are mySaxP. This is the function which takes the dimension of the first parameter is the dimension of the vector, and the second parameter is the scalar variable a, using which we scale up the vector x, and the next two parameters are x and y. The next two parameters are x and y. So what we are doing here is, now we are taking if you just do a time on the whole program, then you can easily see the time taken for the random vector initialization of x, random vector initialization of y, and all these things will be accounted for, and we will lose sight of what is actually happening in this function called maxsaxpy on line number 36. So we put a we use a stopwatch, we take a tick, and after the program, the function gets executed. We call the talk, and we get the total elapsed time between just for this function call. Are you with me here? And the second important thing is the way, so here this only gives time, but if you want to measure like how the cache is behaving when line number 40, when maxsaxpy is getting executed, there is a library called as PAPI, Performance API. So you can, the way we are just taking a snapshot of of time, we can use the PAPI library and instrument code here before and after, and we can measure all the things that perf gives us, like for example, cache misses, cache hits, page faults, anything that you want, you can get. Whereas perf gives it for the whole program. Using PAPI API, we will be able to get only for the section of the code that we are interested in. Okay. Does it make sense? Are you all with me? So these are the two important things that I would like you to keep in mind. One is how to take performance from a section of the code. Second is how we can use PAPI API to instrument your code and get information about specific sections of your code. Well, this is all hard work. You can use Intel tools such as Intel VTune. Intel VTune gives a very clear picture about what is happening in your program. And this is something I would like you to experiment, this Intel VTune. It's a tool. And I think Intel also has a latest tool called as Intel Performance Advisory or something like that. I used VTune, but I didn't use advisory. I will use, and well, perhaps in the next class we can see what's going on there. Okay. So with this, so here in this whole effort, we are trying to, in today's class, we pretty much focused on how to identify bottlenecks in the program and have an estimate on what is the maximum speed up that you can get for your program using Amdahl's law and Gustafsons law. So that is the theme for today's class. But then let's say your potential speed up, that you're using this analysis, using your analysis and application of Amdahl's law, you see that your program should get 10x speed up. But no matter what you are doing, you are able to get able to achieve only 2x speed up. Able to achieve. What could be the problem? Able to achieve only 2x speed. Okay. So what could be a problem? Can you take a guess? What could be a problem that why we are getting only 2x speed up whereas Amdahl's law is saying that we should get to 10x speed up? Yeah, number of the available compute power may not be there to give you that speed up. So how do we estimate? How do we estimate the compute power given by your system? The question is, how do we estimate? Question, we'll stop with this question. How do we estimate? How do we estimate? This is the question which we will talk in the next class. Estimate the compute power of your system. This is the question for the next class. So in the next class, we will do a very interesting analysis on this estimation of compute power and compare it with see whether the problem is with our program or is with the underlying machine that we are working on. So with this, I will stop today's lecture. Any questions? Do you have any questions which you would like to ask, or you're all good? I strongly advise that you use some of these tools, get a feel for them, and it will be great. If there are no questions, we'll stop here.